Hello, my name is Long Sha from Brandeis University. Today, I want to present the neural knowledge tracing for EdNet dataset correctness prediction. Neural knowledge tracing is a work we did back in 2017. We originally proposed this method and experimented on the assessment datasets. So we have this great opportunity to be invited and try out our method to the new EdNet dataset. I want to start with some background on knowledge tracing and the problem definition. So ITS, which is the Intelligent Turing System, has played a great part in education, especially currently when we are in the COVID-19 pandemic. The educational institutions have either adopted fully or hybrid remote learning strategies, including, for example, live streaming, video meetings, as well as some interactive learning activities. So under such circumstance, using student system learning activities to measure students' mastery of knowledge can better help students to diagnose their learning status and help them to learn more efficiently, which comes to the knowledge tracing. We can define a dataset D consists of a list of student S to student Sn. We define list of interactions of each students of xi1 to xit, and each interaction can be composed, for example, of a question and answer, whether it's answered correctly, Q and A. So in that case, we can define a task of correctness prediction as follows. So we want to predict whether a student can answer a question correctly, given his or her previous interaction histories. We can also zoom in more to map the question queue to a list of knowledge tags, which in some cases maybe has some additional features, additional attributes corresponding to the question queue we denote G. So in the knowledge tracing domain, there's a lot of exploration of method historically. For example, there are Bayesian knowledge tracing method, item response series methods, and that along a lot of methods using machine learning and deep learning data-driven method, like we discussed in details in the paper. So here is a bird's eye view of the neural knowledge tracing method we propose. The basis of the model is a recurrent neural network. We also have some special architecture design we found beneficial to the prediction and the model efficiency. The recurrent model here we choose is long short-term memory, also known as the LSTM model, which is very successful in natural language processing, as well as the temporal learning domains. Here on the right side is the inner structure of an LSTM module. If you're familiar with this structure, it has four gating mechanisms highlighted in the graph. Say input forget gate, which controls the inflow of information from the input and the last time hidden cell. And also the cell gate controls the update of the memory cell, and the output gate, which controls the outflow of the memory cell and up until the next time step hidden state. We also use stacking layer setup, which can increase the model capacity with more layers of abstractions. While the residual connection we choose to use can help with the degradation problem that caused with the deeper layer setup. We adopted this from the computer vision community. In our previous work, we have some comparison evaluation studies and found adding these connections can help the model learn faster and converge better. The last part of design of the model is the knowledge to prediction module, which is a very small multi-layer perceptron module that takes the output of network as well as the new question representation. This module is designed in minds of mimicking the interplay of the knowledge status as well as the new question representation. So we want to use that to simulate how the network predict, given the representation status of the knowledge and the new question, to output the probability of whether that representation can answer the question correctly. So upon convergence, we can also use the output the KT as an indirect signal to infer the knowledge status. This can be a byproduct of the model. We experimented on the EdNet KT1 dataset, which also used in the competition on the Kaggle. So the dataset we use is very simple. We use the question and answer tuple set. Each student have a theory of that. We have around 60 million interactions, around 678,000 students, around 14,000 questions, and around 300 knowledge tags. Regarding the experiment, we followed our original work in 2017. We compare our method using two benchmark methods, the simple LightGBM and the deep knowledge tracing. We use a very simple light gradient boost machine without extensively feature engineering, and use a modified deep knowledge tracing method to compatible with the EdNet dataset. We found our neural knowledge tracing method empirically performs better comparing to the benchmark setting, and perform around 0.78 AUC for the correctness prediction. We applied our previous work method on the new dataset and explored the task. We found the method achieved good performance comparing with the simple LightGBM and deep knowledge tracing method. This aligns with our original study on the assessment datasets, but this is definitely not the best performing or state-of-art performance on the EdNet dataset. During the competition, we definitely saw a lot of brilliant teams that using advanced feature engineering, advanced model designs that achieve very, very good performances. We also noticed there are teams that works using recent attention-based, transformer-based models that can also achieve very, very good results. We're very excited to discuss with you guys and learn from you all. Thank you.